So if you want to use your model to predict something so important as the sea level rise, you want to make sure you are confident on your predictions. I hope this will eventually lead to important advance in climate modeling.
This paper is about a computational end-to-end framework that explains how to use available data to train or tune mathematical models to increase their predictive capabilities. The usual view of modeling and simulation is given some inputs, parameters, boundary conditions, source, forcing terms, just about anything that goes into the model. We run this computational model to compute some output. This is the so-called forward problem. The question is, what happens if we don't know these parameters that go into these models? Take, for example, the modeling of the dynamics of polar ice sheets, in particular Antarctica, that we use as application in our paper. How do we model the flow of ice if we don't know what happens underneath the ice? We know what we know, or perhaps we know, that in some places the ice is frozen to the bed or the continent, and in others it's sliding. We can describe the sliding of the ice at the base of Antarctica, but the equation will have unknown parameters. Now, we don't know these parameters, but we do know the flow of ice at the surface of Antarctica, which we can use to find or compute the parameters which, when we plug them in back into the model, will give rise to an output that is consistent with the measurements. This is what we call an inverse problem. An additional question we would like to answer is how much we can trust these inverse solutions. And hence a significant part of the paper is dedicated to answer that question. I see this work as an important, a little but important piece in a big puzzle. And this puzzle, imagine the goal of this puzzle would be to advance research, for instance, to predict the sea level rise with more certainty.